Welcome back. In the previous sections, I have described the 1 dB compression point and the third order intercept point. These are parameters that limit the upper limit of the dynamic range. They limit the maximum power that the receiver can take. Now let's discuss on the opposite. What is the minimum power needed in a receiver? There are actually three aspects that determine the minimum power that a receiver needs. One is the noise and the minimum signal-to-noise ratio specifications. But there are other effects that we will be describing, such as receiver blocking and interference. Let's go for the first one. As you recall, all receivers can be characterized by an equivalent noise temperature, and this equivalent noise temperature determines the signal-to-noise ratio that the receiver will have at the output. And this signal-to-noise ratio would be the power of the input signal divided by the noise at the output. I'm sorry, the output of the input signal, but the noise at the input, including the noise coming from the antenna or whatever source we have, and the equivalent noise of the receiver. Accordingly, if we have at the output of the receiver, we have to deliver a given signal-to-noise ratio, we will have some minimum signal power that we will have to achieve, and this is given by this equation. This minimum signal-to-noise ratio multiplied by K, B, and the sum of the equivalent noise temperature for our receiver, and the antenna temperature, the noise temperature or of the antenna or whatever signal source that we have. I have to say that in many instances, this required signal-to-noise ratio might not be specifically, might not be directly specified. It may be an indirect specification, for example, through another parameter such as the bit error ratio or another parameter related to the quality of the signal, right? And another thing that I want to point out that in many references you will see the acronym minimum detectable signal. And this minimal detectable signal has several interpretations. Sometimes it can be interpreted with S-min, as I've wrote in this equation here on the side, or the S-min for a specific signal-to-noise ratio. It may be 0 dB, or maybe some other value, 3 dB, 10 dB, or etc. Right? So we will not be using this acronym minimum detectable signal. We will be using S-min to understand that the minimum signal power for which we achieve the minimum signal-to-noise ratio. However, I point out that there are other specifications that might affect that minimum signal power that we'll need at the receiver input. And these are written in this slide. One would be the minimum power to drive the successive stages in a system chain, or maybe the minimum power to overcome a drop in receiver gain caused by an interfering signal, which is a case that we will see later on, or also we might have some requirement of minimum power to overcome the interference either from our own transmitter or from other sources, and this is a case that we will also be looking at later. Now, we have also already seen the case of where the minimum signal is specified by the signal-to-noise ratio, and now let's examine the case for receiver blocking. And for this case, we will use this general equation that we used before to relate the output of a nonlinear system subject to an input of the system where the input is composed by the sum of two tones at different frequencies. Now imagine that the tone at frequency omega 1 describes our desired signal, and the tone at frequency omega 2 is an interference signal. And assume a very unfavorable scenario where the amplitude of the interfering signal is much stronger than the amplitude for our signal. In this case, if we focus on the output of our system at the frequency, at the desired frequency, at the frequency of our desired signal, we see that this amplitude depends not only on A1, which would be this term and this term, but also on the product of A1 by A2 squared, right? And recall that A2 is much stronger than A1. So let's look at what happens in this case. Now in this case, we have that this amplitude of the output signal at omega 1 would be this term. And now this term we can consider that it's negligible if the amplitude A2 is much bigger than the amplitude A1, and therefore the overall amplitude of the signal at omega 1 would be K1A1 multiplied by this factor, right? And recall that in this factor K3 is negative and K1 is positive, so this is a negative term, right? So what will happen here is that this amplitude, as A2 is increased, this amplitude will be decreasing the overall power of the signal at frequency omega 1, and that might give us problems in our receiver. So let's, for example, examine when the power gain falls 3 dB. This happens when this term is equal to 1/2, and if you do this mathematical derivation, this happens. This mathematical derivation is used to find out for what amplitude of A2 this power gain of 3 dB happens, right? So this power, which is called the power of the jammer, can be shown to be proportional to the 1 dB compression point of our system, right? It's actually 1.20 dB higher than the 1 dB compression point, right? And for this particular value of jamming power, we would have to increase the power of our input signal 3 dB more than what would be actually required to compensate for the drop in gain, right? So this is another limitation of a system, right? Also, we can have a scenario where we have interference, and this is qualitatively shown in this slide. In this slide, we have a transmitter chain and a receiver chain. They may be connected by a duplexer. And here in the receiver chain, I show the received signal. The received signal may be picked up by the antenna, and this received signal has a given spectrum, and this spectrum might be threatened or by an interfering signal coming also from the antenna, right? And of course, the minimum power of the interfering signal has to be high enough to overcome the interference. Besides that, the interference can be coming also from our own transceiver, right? Our own transmitter, right? So because this duplexer may have some transmitted power leaking into the receiver chain, and therefore at this point we might have a spectrum just as this. So the receiving signal has to overcome both the interference coming from the outside and the interference created by our own transmitter, right? And both these powers can be very high. For example, in a 3G mobile handset, the ratio between transmitted and received power can reach to about 116 dBs. This is between 11 and 12 orders of magnitude, which is very, very high. And therefore, for this to work, the transmitting frequencies have to be far enough from the receiving frequencies so that the signals do not overlap in power. And the same thing happens for the interference frequency. People have to radiate at frequencies sufficiently far away from our received frequencies so that this interference can be tolerated. Also, interference can be combined with nonlinearities, right? Sometimes what happens is that we have an interfering signal whose spectrum would not overlap with our received frequency, but it happens that our receiver is very nonlinear, and therefore all this spectrum that should have been decaying decays much more slowly, because here we have intermodulation products at 2f2 minus f1 that are much stronger. The spectral content at this frequency is much stronger than it would be just because of the effect of the intermodulation products. In other words, there's some spectral regrowth of the interference due to the receiver nonlinearities, and that can also mask our received frequency. Another aspect that can happen is that what's shown in here, we have our desired signal compared with a very strong interference, and those two signals do not overlap in spectrum, but when we pass this signal through a local oscillator, it happens that the local oscillator has some spectral impurities. Typically, local oscillators have some phase noise, and then this phase noise is reproduced after mixing with the input signal. This phase noise at this point is reproduced at each one of the spectral lines that we had at the input, and by doing that, the combined spectrum of the interfering signal and the phase noise of the oscillator can mask our desired signal. So, in summary, the minimum signal can be set by many aspects, right? The most fundamental one is noise, that we have to achieve a given signal-to-noise ratio, but there are also other aspects that can affect that requirement. One is to overcome interference and the receiver blocking effect, and also to overcome the interference caused by the transmitter and some adjacent channels to our system. And that concludes this section of the lecture.